So hello guys, welcome to our new video in the series of psychometric based numerical. In this video, we will see another example of a numerical based on the psychometric chart. In this video, we will see how the different parameter can be calculated for the air conditioning system design. So now we have taken one problem. We will see its explanation. Now in the air conditioning system is to be designed for a restaurant with the following data. So here data is given, so we have to design the air conditioning system for the restaurant. Now outside design condition are given, which is 40 degrees Celsius dBT and 28 degrees Celsius WBT, and inside design condition is given, which is 25 degrees Celsius and 50% relative humidity, which is human comfort zone. Now solar heat gain through walls, roof and floor, which is 5.87 kilowatt, and solar heat gain through the glass, which is 5.52 kilowatt. Here occupants are given 25. Sensible heat gain from a per person is 58 watt and latent heat gain is 58 watt. So here heat gain is given same. Now internal lighting load, which is 15 lamps are there of 100 watt each. Now 10 fluorescent tubes of 80 watt each. Now total there are 15 lamps of 100 watt and 80 tubes, 10 tubes of 80 watt. So this lighting load is given, and sensible heat gain from other sources given as a 11.63 kilowatt. So this we have to must add into our calculated heat load. Infiltrated air is 15 meter cube per minute. The volume flow rate is given of infiltrated air. Infiltrated air can be from other sources, crack walls and windows or doors. Here, if 25% fresh air and 75% recirculated air is mixed and passed through the conditioned coil. So here recirculated air and fresh air ratio is given, which can be 1:3. Now we have to find the amount of total air required in meter cube per hour, the dew point temperature of the coil, the condition of supply air into room, the capacity of the conditioning plant. Now they have given that the dew point, bypass factor is given 0.2. Here for the solving the numerical, first we have to take one psychometric chart and then we have to draw indoor and outdoor condition whichever we have given, and then draw the schematic. Because air mixing problem is given, as we can say fresh air and recirculated air is mixed, so we should know if the air mixing is before the conditioning or after the conditioning. So the problem will be differ by this single point only. Now in the solution we can see given are the given values are the taken down here. Bypass factor is 0.2, volume flow rate, another heat load or other things are written down here. In the adjacent diagram we can see the uh, diagram here, where outside air condition is given, recirculated air condition is given, then mixing will happen at the point number 3 and then it will pass through the coil, then we will get point number 4 air. Now that condition air of point number 4 will be passed into directly room. The room desired condition is given as TD2 should be 25 degrees Celsius and humidity should be 50%. In this way we have to solve the problem. So initially what we can do, first we have to take a psychometric chart, and so here we can see initially draw point number 1, which is our outer point. Outer point is given 40 degree dBT, and it's what we have given for point number 1 WBT and DD. Now in this way, here WBT is 20 degrees Celsius and DBT is 40 degrees Celsius. In this way we can draw our point number 1. Same for the point number 2. Here we can see we have 25 degrees Celsius dryable temperature here and 50% relative humidity. So here humidity ratio lines are like this. This curvature line would be there, and this curve line is for 50%. So where they intersect, That should be our point number 2. So initially we have to just draw 2 points, point number 1 and point number 2, and after that we have to calculate the mixing point and then point number 3 in between the point number 1 and 2. In this way we can draw. So now we have a volume flow rate of air, so we have to calculate in the in the form of meter cube per minute. So from the psychrometric chart we can find the specific volume of air at point number 1. Specific volume, how we can calculate? Here, this is point number 1. So specific volume, between the chart there some inclined line are given. These are the for the specific volume lines. Now at the point number 1 we can get the specific volume at the point number 1 from the error trial and error method or from the just seeing in the chart. So now at the point number 1 we get as volume for specific volume we get 0.914 meter cube per kg of dry air. Enthalpy at point number 1, H1 get 90 kilojoule per kg of dry air. Enthalpy at point number 2, which is 50 kilojoule per kg of dry air. Now enthalpy at point number A, HI is drawn here. So between the point number 1 and 2 on horizontal and straight line, vertical line are drawn, and their intersection is given as a point number A. So that would be easy for us to calculate the sensible heat and latent heat. Now we have volume flow rate, so we have to calculate the mass flow rates. For that we have to divide the volume flow rate with the specific volume. Now for the calculating mass at the point number 1, we can divide volume flow rate at point number 1 and specific volume. So we get 16.41 kg per minute. In this way, sensible heat gain due to infiltrated air. Now we get the mass flow rate, and when we have just enthalpy difference of between point number A and point number 2 will give us sensible heat gain. Sensible heat gain, how much we got? Which is nearly about 262.56 kilojoule per minute. Now we have to convert it into kilojoule per second, so that will give us into kilowatt. So in kilowatt we get 4.376 kilowatt. Similarly, latent heat gain we can calculate. So we just have to take the difference between the point number 1 and point number A and multiply with the mass. So we get as 6.564 kilowatt. Total sensible heat gain from the occupants, we can calculate number of occupants multiply by uh, heat gain. So we get 1.45 kilowatt, and total latent heat gain from occupants is 1.45 kilowatt, which is same because both latent heat and sensible heat gain are given as 58 watt. Here sensible heat gain due to internal lightning load. So there they have given 15 lamp and 10 tubes. So total heat we get as 2.3 kilowatt here. Now we know that the sensible heat gain in the room. So total room we can add all these values. So we get 31.164. Here important point is here we have to add 11.63 kilowatt because in the numerical they have given that extra heat is added, so it should be added here. Similarly we can calculate the room latent heat, that would be 8.104 kilowatt. So we are having the sensible heat, we are having the latent heat, so we can get room sensible heat factor. Room sensible heat factor, how we can calculate room sensible heat upon room total heat. So in the room total heat, sensible heat and latent heat both are added. Now we get the room sensible heat factor as 0.795. So we can draw just a form of point number 2 here. In the chart we can see here nearly, if you see the chart there you will get a semicircle here, and in there some values are given. So how much value we get? 0.795. Just have to take the scale, ruler scale here, and just the drag here at the point number 2. So this line we get here. room sensible heat factor line, or another ways, if you are using the another chart, in some chart you may get the room sensible values are in between the chart in the form of this inclined line. So similarly you can just take here ruler scale and measure here and drag the at the point number 2. So just join the point number 2 to the saturation line, so you will get room sensible heat factor line. So room sensible heat factor line is very much important line in the problem, which will give us a ADP, coil ADP, as well as the condition whatever we are supplying to the room. So this line is very important. So till here we have calculated the room sensible heat factor and drawn into our chart. So now they have just given us the recirculated air and fresh air ratio. So just we can take the 2/3 of length and multiply it with percentage. So now after the taking the ratio, you can just find here the point which get at the between the 1 and 2, which is 3. Okay. So now also you can see they have just given that the in the numerical, you can see here 75% should be recirculated air and 25% should be fresh air. The ratio of recirculated air is more, so point should be temperature should be inclined towards the recirculated air point. So we can just simply see here point number 3 is exact near to the point number 2 rather than the point number 1. So in this way you can also cross check your value if you are whether you are getting correct or not. So now we got the now point number 3, which is mixing point. Once we get mixing point, you just follow down or write down the values. We have TD3 is 28.8 degrees Celsius and enthalpy at point number 3 is 60 kilojoule per kg of dry air. Now just point number 4 on a line. So for this we have to mark in so for that we should know the bypass factor. Simply here in the chart you can see here initially we draw the point number 3. Now we have room sensible heat factor line and point number 3. So we have to just draw the line in a such a way that the bypass factor we get as 0.2. So this is a very important point for the bypass factor. Yeah. Okay. Now the formula for bypass factor is TD4 minus TD6 upon TD3 minus TD6, because we are calculating the temperature difference between a point number 3 and point number 6. Point number 3, which is we are having mixing point. Point number 6 is saturation point, and here TD3 TD4 is its room condition, means point number 4. Because in the diagram also we can see here we are having a point number 3 and point number 4. In between there is a coil, so coil should be point number 6. Now we get in this method we are using here a trial and error method, in which we have to just put the value of TD6 and TD4. So we should get nearly point, or should be satisfy the equation of 0.2. So in the trial or error method, we will get the value of TD4 as 14.4 degrees Celsius drivable temperature, and TD6 we get as 10.8 degrees Celsius drivable temperature. Now we are having values of all the temperature TD4 and TD6. TD4, which is supplied condition. So we can see here. Yeah, here is TD4. Now you just have to intersect or join this line. This line is also called as the grand sensible heat factor. Yeah, here we go. We are having the all the points TD4 and TD6. Now the point number 4 represent the condition of air leaving the coil or entering the room. The point number 6 represent the dew point temperature of the coil. From the psychrometric chart we can find the enthalpy at point number 4. So H4 we get as 36.5 kilojoule per kg of dry air. A specific volume at a point number 4 we are having 0.626 meter cube per kg of dry air. Our first question was to calculate the amount of total air required in meter cube per hour. Now amount of total air required in meter cube per hour, let's suppose VA. Now MA, we are having a total room heat upon total heat removed. So for this we have to just total heat removed is nothing but enthalpy difference between the points number 2 and 4. The point number 2 and 4 represent the actual removal of a heat from the coil by the coil. Now room total heat is room sensible heat plus room latent heat and divided by H2 minus H4. So in this way we can get mass of air Ma, which is 10440 kg per hour. We just have to multiply it with the specific volume. So we get as 8623.4 meter cube per hour. So they said to calculate into meter cube per hour. So that is the air required. Now dew point temperature of a coil. So previously we have calculated that the by the trial and error method, and we get the TD6 as 10.8 degrees Celsius. Condition of supply air into room. So similarly from the bypass factor and this we got the TD4. Now just we can find another parameter at the point number 4 intersecting point. So we can simply calculate the humidity ratio, which is relative humidity is 88% at that point. So TD4 is 88% relative humidity and 14.4 degrees Celsius dBT. Generally the point number 4, or we can say the point air which is entering the room, that would be having the high humidity, and temperature would be nearly near to the uh, dew point temperature of a coil or apparatus dew point temperature, we can say ADP. Now our next question was capacity of conditioning plant. We know that the capacity of conditioning plant is given as Ma into H3 minus H4. In this way we can calculate our value. We get 39.15 kilowatt. So 1 ton of refrigeration is nearly 3.5 kilowatt. So we can calculate into terms of ton of refrigeration, which is comes out 11.2 ton of refrigeration. So in this way we can solve any numerical based on the air conditioning system design. So thank you all for the listening. So that's all for today.